All right, so yesterday we went over, or we reviewed what an ionic compound is. Okay, so any chemical compound containing a metal and a non-metal. Okay, we talked about the nature of the ionic bond. Okay, and that is that electrons are donated by the metal, okay, and accepted by the non-metal. Okay, that leaves a positively charged metal ion and a negatively charged non-metal ion. Right? We reviewed the naming parts. Okay, so we reviewed that you name the metal first and the non-metal second, and that you make the non-metal's name end in I. Right? All of that was reviewed. Then we started something new, and we started, how do we name ionic compounds that involve a multivalent metal, or a metal that has more than one possible charge? Right? The problem there was that we could have two chemicals that have different chemical formulas, but that would have the same name. Okay, which is obviously going to be a problem because that's like having two people with exactly the same name who are very different. Okay, so we established then that what you have to do is determine the charge on the metal and then denote that charge with a Roman numeral in the name. Okay, so the ones we looked at yesterday, okay, were iron oxide and iron oxide. Okay, we obviously can't have both of those having the same name because they are obviously different. So what we said is you always look at the non-metal. Okay, there are no non-metals with more than one possible charge. So we can always get started by looking at the non-metal. Okay, oxygen, because it's in group 16, has a -2 charge. Okay. What overall charge do all ionic compounds have to have? 0. Okay, so that means the number of negatives and the number of positives has to be equal. All right, if I've got one oxygen with a -2 charge, I have to have one iron with a +2 charge. All right, so this stuff then was called iron Roman numeral 2 oxide. Okay. Sometimes you have to go and do a tiny bit more math, okay, to arrive at that, like in the second example here. All right, we start with oxygen, it's the non-metal with a -2 charge, but this time there are 3 oxygens. So how many negative charges do I have in total? 6. Right, okay, so I've got a -6 charge over here. My whole compound has to equal out to 0, so that means I need to get +6, or 6 positive charges from how many irons? 2. So what is each iron's charge? 3. 6 divided by 2. All right, so then I go iron Roman numeral 3 oxide. Okay, is that ringing a bell from yesterday? Okay, try the 2 at the top. Okay, give you a couple minutes here, and then we'll go through those. All right, so let's look at our first one here. So we'll start it out with the regular ionic naming rules. Ni stands for nickel. Okay, and N stands for nitrogen, so this will be nickel something nitride. Okay, once I've written that out, then I want to double check, does this one need a Roman numeral? So I go over here and I see that yes, in fact it will, because nickel can be a 2+ or 3+ charge. Okay, and that's the only time I use a Roman numeral. Okay, I wouldn't use a Roman numeral for anything over here because they only have one possible charge and it's not necessary. Okay, all right, so nitrogen is in group 15, which means it has what charge? -3. Okay, so every nitrogen is a -3, and there are how many nitrogens? 2. So how many negative charges do I have? 6. I've got 6. All right, so -6 over here, so I've got to get +6 from my 3 nickel atoms. 6 divided by 3 is 2. So this is nickel 2, right? Nickel 2 nitride. Okay, is that making sense? All right. Then we've got bismuth and oxygen. All right, so we'll go through our usual naming rules. Okay, we name the metal first, we name the non-metal second, make it end in "ide." All right, and I'm going to need a Roman numeral because bismuth can be a 3 or a 5, right? Yeah, 3 or a 5. So, every oxygen is -2. And I have how many oxygens? So how many negative charges do I have? 10. Right. Okay, so I've got -10 here, okay, and I've got to get +10 out of these 2 bismuth. So what's the charge on bismuth? 5. Right, so this would be bismuth V oxide. Okay, so remember I said, like, if you know to 4, you're probably pretty good, but 5 might be a little bit better. Okay, and so you probably don't need to know past 5, because there's like 2 things that are more than 5 on the periodic table. Okay, all right, everybody okay with that? All right, let me throw another wrinkle at you. What would you call that?
Lithium iodide?
Lithium iodide would be this, right? Because it would just be an element, okay? This has more than 2 elements in it, doesn't it? Okay? Thought ionic compounds were supposed to be a metal and a non-metal. Is this not an ionic compound? It's still an ionic compound.
Yeah, it has a metal in it.
It does.
Ionic.
It has to be ionic because it has a metal in it, yep.
Lithium dioxide.
Close. Okay? Sometimes what we close. Okay? Sometimes what we get with ionic compounds is that we get strange polyatomic ions involved. Okay? So up here on the top of your periodic table is a list of common polyatomic ions. They're just groups of atoms that somehow hang out together but don't have enough electrons to keep everybody happy, so they have a charge. Okay? Most of them are negatively charged. In fact, I think there's only one in here. Yeah, just ammonium that's positive. Okay? The rest are all negative. If they're negatively charged, then they behave like the non-metal part of the ionic compound. Okay? Because the metal obviously has a positive charge. Okay? So, what I want to do is if I see something like that, it starts with a metal, I know that it's ionic. If it's got more than 2 elements in it, then I've got to look to here and see if I can find that other combination in here. All right? So if I look down the chart here, I can see here's IO3. Okay? It says it has a -1 charge, and it's called iodate. Now, the naming of this is actually easier. You don't have to do any thinking. You don't have to change the ending of this. This is how you write it in the name. So this stuff would be lithium iodate. Okay, so if you have a compound that starts with a metal, it's ionic. If it has more than 2 elements, you'll have to look at the periodic tables, or sorry, the table of common polyatomic elements, or ions, and find the ion that fits, okay? And you'll be able to find it there. Okay. Let's try a different one. Let's see. Okay, what's the BE stand for? Beryllium. Okay, so that part doesn't really involve too much thinking, right? What is OH? Hydroxide. So this stuff is just beryllium hydroxide, yeah. Okay, we still don't put in any prefixes. Okay, we just put in the name, all right? And remember, the ones in the polyatomic chart do not get their endings changed. Whatever they're written as there, copy it. That's how you write it. Okay? Now, why is the hydroxide in brackets?
Because the 2 represents, like the 2 that's in the back of the brackets represents that there's 2 of each of them.
Right. It says there's 2 hydroxide ions, because according to that chart, the charge on hydroxide is -1. Okay? And so we would still have to do that whole charge balancing thing that we do with all ionic compounds. This is an ionic compound, it has to have an overall charge of 0. Okay? Beryllium has a 2+ charge, and hydroxide is a -1. Okay? So I need 2 hydroxides in order to make the charges balance. Okay? So why would I put the brackets in? Why don't I just put a 2?
Because then it would only apply to the hydrogen.
Exactly. Okay? It would only apply to the hydrogen. This and this are not the same thing. Okay? This one is a beryllium atom, okay, connected to 2 hydroxide ions. That would be 1 oxygen and 1 hydrogen times 2. Okay? This is a beryllium atom bonded to an oxygen atom bonded to 2 hydrogen atoms. That's different. Okay? So we use the brackets just like you use them in math, okay? So that 2 applies to everything in the brackets. Okay? Question?
Is hydroxide an ionic or molecular?
It's ionic. Anything in the table of polyatomic ions is by definition ionic. Okay, it's a charged particle, right? Something is molecular if it works out and they're sharing the electrons. Okay, what would this stuff be? Water. Yeah, that's water. Water is weird, okay? It is a molecular compound, but can sometimes behave ionically. You'll learn very quickly that if there's a rule in chemistry, water's the exception, okay? Yeah, everything depends on water. All life depends on water because water has all these strange properties about it, okay? So we can write water like this, which makes it look like a molecular compound, which it is, okay? But we can also write it like this, because if you combine it with an acid or a base, it behaves like it's ionic, okay? And it does these strange things. So it'd be a hydrogen ion and a hydroxide ion, okay, instead.
So you could call water hydrogen hydroxide then?
You could, but I'd just write water. That's just me, but I would just, it's shorter and I don't spell it wrong and yeah. Okay. All right. Is that making sense to everybody? All right, okay. Then, what I want you to do, this is where, oh, where did it go? Sorry, I thought I had a list of some that were a little bit of all of them. Yeah. No, that was our other list we did already. Okay, some of each. Okay, well, let's talk molecular compounds then. Okay. If we're naming molecular compounds, okay, so molecular compounds work differently, obviously, than ionic compounds. There's no metal in a molecular compound. It's made of 2 non-metals. Okay? Now, all non-metals have what charge? They're all negative. Okay? So is there any way to balance the charges or trade electrons so that everybody's happy? There really isn't. Okay? They all need electrons to fill their outer shell, so there's not going to be any trading of electrons. Okay? What nonmetals do when they bond to each other is to share them. Okay? That makes the bond much stronger. Okay, so we were talking about the ionic bonds and we said, yeah, they're weak because everybody gets what they want and there's no reason for them to stay together. Well, molecular bonds are much different. Okay? In a molecular bond, the bond is very strong because the 2 parts depend on each other. They have to share the electrons. okay? And so as a result, they stay together much better, okay? But that means they do things a lot differently than ionic compounds. They're typically less soluble in water, okay? If they're in water, they're not gonna conduct electricity, okay? Things like that. So what we end up having then is electrons that are shared, right? In a water molecule, for example, okay? You got the two hydrogens and you got the oxygen atom. So oxygen normally, okay, has its inner shell that has 2 electrons, and then it's got its outer shell that has 6. Okay? These 2 electrons that are alone are where the hydrogen atoms are going to bond. Okay? So the hydrogen atoms come in and they bond in this position and this position, like you see here in this diagram, and those electrons are shared. Okay? Hydrogen gets a second electron in its outer shell. Now its outer shell is full, okay, and it's happy. Oxygen does that with 2 hydrogens, and it gets its 2 open spaces filled and shares those electrons, and so its outer shell is full. Okay? That sort of makes sense? So those bonds end up being much, much stronger because those non-metals don't want to let go of each other. Okay? If they let go of each other, their life will be empty. Okay? Because they'll lose that thing they were getting from that other element. Okay? And then their outer shell won't be full. Right? So that bond is much, much stronger. Since there's no balancing of charges, is there any real rule as to how many of one element can bond to another element? Not really. Okay? It's not like in an ionic compound where there's only one way beryllium and chlorine can go together. Okay? In a molecular compound, there's any number of ways. That's why in their names we use prefixes. Because we have to say, in this compound, there's 2 sulfurs and 1 oxygen, or whatever it happens to be. Okay? We have to denote the numbers because there isn't a rule or a hard set ratio for those 2 things to bond to each other. All right? So in these ones, we do have to use the prefixes in the names. All right, so all you need to know about a molecular compound's bond is that it's very strong because the electrons are shared. Okay? That's really the extent for science 10 that you need to know. So when we name a molecular compound, okay, we've got 2 nonmetals, okay, and we simply name it in the order in which it's written. Okay, so the first nonmetal gets its name written normally, and the second nonmetal gets its ending changed to I. So similar to an ionic compound, okay, it's just this time they're both nonmetals. And we got to put prefixes in. Okay, now all prefixes apply to the second nonmetal, but the first one you don't always have to use mono. Okay, so you'd never have like mono sulfur mono oxide. Okay, you would never write mono on the first one. I don't know why. Talk to the chemists. I feel like they just need to be difficult. Okay, on that one, but okay, you never use mono on the first non-metal. Okay. All right. So if we're looking at some of these here, if I got carbon and sulfur, okay, there's only 1 carbon, so I just write carbon. Okay, there's 2 sulfurs, disulfide. Right. In this one here, I've got 2 nitrogen, so dinitrogen. Oh, and that's wrong. What did I have in front of this? Mono. Okay. Or sometimes we just write monoxide. Okay. And then for this one here, P4O10, that would be tetraphosphorus deca oxide. All right.
That's not the
What's that?
nothing.
So you're going to need to know your prefixes to 10. Here's the good news. They're all pretty much the same as the shapes. Okay, like so if you know all your like geometric shapes up to 10, you're fine. It's the same prefixes. Okay, but just in case, I'll give them to you here and you can write them down. This is something I will allow to be on your periodic table. Okay, if you want to have the prefixes on your periodic table, I'm okay with that. All right, so 1 is mono, 2 di, 3 tri. Okay, and this is where they kind of go like the shapes from here. Okay, 4 is tetra. 5 is penta. Okay, 6 is hexa. What's 7?
Hecta.
It's hepta. Okay, and I'm gonna tell you that right now, only because if you took it in French, you probably learned that it's septa, okay? Or maybe someone along the way told you it's septa. But Mr. Reel, who teaches chemistry 20 and 30, hates that. I don't know why, okay? But it's like triggering for him, and you don't want Mr. Reel triggered, okay? It's like scary. So, you don't want that. So it's hepta from here on, okay? And we will never speak of the other one again. Hepta for 7. Okay, 8's octa, 9's nona, 10's deca. And you won't be asked for anything beyond 10. Okay, now there is one thing that we do have to be mindful of. There are molecular compounds, that's the rules we just went over for naming, and then there are actually molecular elements. Okay, some elements bond to themselves in small groups. All right, so hydrogen is an example of that. You never find hydrogen just H by itself. Okay, it's always bonded to another hydrogen as an element. Okay, so this stuff, we don't change the name, it's still, because it's all still hydrogen, it's just hydrogen. Okay, same with oxygen, nitrogen, chlorine. In fact, there are a whole bunch of them on the periodic table all together here. All right, so starting with nitrogen, okay, you got nitrogen and oxygen, which are both going to come as a pair. Okay, every non-metal in group 17 comes as a pair. Okay, so you have N2O2, F2, Cl2, Br2, I2, At2. Okay, hydrogen also comes as a 2. Okay, and then you've got phosphorus, comes as a 4. Sulfur comes as an 8. Okay, those are our molecular elements. Just because you see this doesn't mean you call it octasulfur. Okay, that's just sulfur. It's 8 sulfur atoms, but it's still only sulfur, so we don't use any compound naming rules. Okay, it's a molecule, but it's not a compound. Does everyone follow the difference between like compound and molecule? Okay, compounds are all molecules, but not all molecules are compounds. It's one of those weird exception things. Okay. Right, so that's why we call those the molecular elements, because they actually come as a molecule in their natural state. Okay? But we don't apply the naming rules to them.
So you don't name those ones?
No, that's what we're saying here, is
Yeah.
that when I see H2, I don't go dihydrogen. It's just hydrogen. Okay? If I see O2, it's not dioxide, it's just oxygen. Okay? Because they're not compounds. I only use these rules to name compounds. All right, let's have you try the first 4 here. Okay, write down the proper chemical names using your molecular naming rules for those 4. So for the first one here, I've got nitrogen and iodine together, so the rules say I don't change the name of the first element, so I just write nitrogen. There's only one nitrogen, so I don't need a prefix on that one. And then what prefix do I need on the iodine? Right. So triiodide. I always put a hyphen in because it looks funny if I don't. Triiodide. I think it's supposed to be hyphenated. But I don't know. I wouldn't mark it wrong if it wasn't, because I don't teach English. All right. For number 2, how many carbon do I have? Just one, so I don't need a prefix on that. Okay, carbon, and then I have 4 iodines, so now it's going to be tetra. That would also require a hyphen. Tetraiodide. Okay, number 3. So I've got 2 nitrogens. Do I need a prefix this time? Yes, I do. Anything other than 1. So dinitrogen, and then number 4, no prefix on tellurium. Okay, and then diacetyl. I keep forgetting the hyphen in, so I put it in after. So, diacetyl. Okay, is that ringing a bell from last year?
Yep.
Okay, and there's not gonna be anything more complex than what you learned last year for molecular compounds. Okay, there's no special things that you haven't done before like there were with the polyatomic ions and the multivalent metals. Alright, so let's have you try another 4 here, okay? And then we'll move on to a list of them that are, some are ionic, some are molecular, some have polyatomic ions. Okay, and then we'll start looking at writing formulas. We may not get to the formulas today. So our first one here, we got 2 phosphorus, so we're gonna need diphosphorus. Phosphorus. Okay, trisulfide. Okay, what about number 6?
Oxygen monosulfide.
Oxygen monosulfide. Number 7, we got 3 silicone. So what prefix do I need there? Tri. Tetraphosphorus, right? Phosphide, yes. Okay, and number 8. So I've got 1 sulfur. Do I need a prefix? Sulfur, dichloride. All right, so those are pretty straightforward. All right, the trick comes when you start getting a list or you start getting some randomly and you know, I don't tell you these are all ionic, or these all need a Roman numeral, or these all have polyatomic ions, and you have to go, all right, that one's molecular, that one's ionic and needs a Roman numeral, that one's just ionic, that one has a polyatomic ion in it, and then applying the appropriate naming rules, okay? Because that's what you're gonna get on Tuesday's quiz, okay? You're gonna get some of everything. Okay, so let's have you guys try on here the first 6. Okay. So, some are ionic, some are molecular, some need Roman numerals. No polyatomics in that one, but. All right, give you a few minutes there, and then we'll go through them. So when I'm getting a list where I don't know that they're all one type, okay, the first thing I have to do is decide what type of compound is it. Okay, so on that first one, is that one ionic or molecular? How do I know? It's got a metal in it, right? Okay, it's got a metal in it, especially listed first. Okay, it's going to be an ionic compound, so I'm going to name it according to the ionic rules. Okay, so I'm going to name it lithium. Okay, and then chloride. And then I better check something. What do I need to check?
Whether it's a multivalent.
Yeah, exactly. Whether it's a multivalent metal and thus requires a Roman numeral, does it? No. No. Okay, lithium only has 1 possible charge, so we're done with that one. All right, what about number 2, ionic or molecular? Ionic, chromium is a metal. Okay, so I'm going to apply the ionic naming rules. Chromium, fluoride. Does it need a Roman numeral?
Yes.
Yes, it does. Chromium could be a 2 or a 3, right? Okay. All right, so I need to look at my non-metal. Okay, fluorine is always a -1, and there are 3 fluorines, so that means I have 3 negative charges. So I have to get 3 positive charges, and I only have 1 chromium to get them from. So that chromium has a charge of 3. So this is chromium 3 fluoride. Okay. All right, number 3, ionic or molecular? It's molecular. Phosphorus is a non-metal, bromine is a non-metal. Okay, we have 2 non-metals together here. So I follow the molecular naming rules. Phosphorus, okay, and tribromide. Questions on that one? Okay. Is number 4 ionic or molecular? It's ionic. Zinc is a metal. Right? So we'll follow the ionic rules. Zinc iodide. iodide, does it need a Roman numeral?
Nope.
No, zinc only has one possible charge. It's always a 2+. Number 5, ionic or molecular? Molecular, okay, they're both nonmetals, so silicone doesn't get a prefix because there's only one. What prefix goes on oxide? Di. And then number 6, ionic or molecular? Molecular, okay, carbon is a non-metal, right, so this is going to be carbon tetrasulfide. Okay, making sense? All right, I got a few more on here, and some of them are going to have the polyatomics. I think I put a few in here that have polyatomic ions. Yes, I did. Okay. So we'll skip 7. Let's go to 12. Should be able to get that done before the bell goes. So number 8, what are we looking at for a name for that stuff?
Sodium hydroxide.
Sodium hydroxide. This is the active ingredient in oven cleaner. Okay? It is highly basic, okay? Very corrosive. That's why it can dissolve the crud that's burnt onto the sides of your oven. Okay? Number 9, what are we looking at?
Calcium sulfate?
Calcium sulfate. What's wrong with the way I wrote that formula? Yeah, I don't need the brackets, right? I didn't put a number outside of them. There was no need to have them there, okay? I would only use brackets if I wanted to write another number out there. In this case, I don't need to, so the brackets are unnecessary. It's not necessarily wrong, but they're unnecessary, okay? All right, what about number 10?
Potassium permanganate.
Potassium permanganate. All right, this stuff is interesting. It used to be used as an antifungal. And they would give it, people would rub it in their feet or stuff, especially soldiers during like World War I and II, and would keep them from getting like fungus on their feet. But it had this unfortunate side effect. It's these pretty little purple crystals, okay? But if you get it on your skin, it reacts with your skin and it stains your skin, okay? So if you're very fair-skinned, okay, the effect is quite obvious. It stains your skin brown. Okay? If you already have dark skin, you probably wouldn't even notice it happen. Okay? But I once had this kid who never ever listened to me. Brett, who never listened to me, not ever. We did a lab and it had potassium permanganate as one of the compounds. And it's pretty stuff. And I said to the kids, make sure you don't handle this stuff. Okay? If you're very fair skinned, it's gonna turn your skin like brown and it'll be very noticeable. And so he started playing around with it. He brings it up to me. He's got the whole dish. And he's doing this with it. And he's getting like right up to here on his fingers. Okay? And remember, this guy is like pasty. Okay? And he's like, Coderre, this stuff is so cool. I'm like, Brett, what did I tell you not to do? I don't know. Look at your fingers. Up to the first knuckle. Dark brown. Like, he was like, you know, where have your fingers been? Dark brown. Okay, like I said, he was really fair skinned. He was really pasty white. He had this dark brown stained fingers, the first 3 fingers in his thumb. Like, and it doesn't come off. You can't wash it off. It has to, like, you have to exfoliate. It was like weeks, okay, before it came off. He still never listened to me. I would have thought that would have taught him a little bit of a lesson because everybody made fun of him for like 2 weeks. Like, what are you doing, man? Because he had this brown fingers. Whatever. It didn't change his habits. Okay. So with number 11 here, nitrogen monoxide, molecular compound on that one. Okay, and for number 12, okay, we have another polyatomic ion.
Beryllium cyanide.
Beryllium cyanide, highly poisonous. Okay, have a good weekend, guys. We will see you on Monday and start working on chemical formulas.